Wonderful. Okay, folks, so today is your review day for Unit 3. Let's talk about the Unit 3 test, which will be Friday. So this test is currently slated to be about 75 points. I might tweak that a little bit tonight. And it should be about 19 questions. Might tweak that also tonight. Okay? Now, generally speaking, here's what will be on it. There will be some math on there. For sure. It won't all be math, but there will be some math. So you better be able to get me the Q, the M, the C, or the delta T in your sleep, all right? And you got to be able to slap some units on there. So if you're like, the answer is 12, I'll be like, 12 what? 12 degrees Celsius, 12 joules per gram degrees Celsius, 12 L's, which is what you will take on this test if you forget your units, okay? So just make sure you know your units. I'll ask you to put units on any calculation that you are requested to do. Anyways, labs. So you need to be familiar with any lab that we did this unit, okay? So stuff like, it won't be like, hey, what metal was the lab that we did in lab? Like, I'm not going to ask you to memorize that kind of thing, but I will ask you like, hey, remember the heat capacity of the Bolt lab? We boiled it, put it in a cup of water. Like, you need to understand the general happenings of what went down in any given lab and the concepts that we learned. So the Q to Q, that kind of stuff. Oh yeah, so with math, back to that by the way, Q equals MC delta T problems, Q to Q problems, so you might have to solve the heat capacity of a sample or something like that, and 5 Qs. I promise you there will be a 5 Q on there. It might not have 5 total Qs, so it might only be like 3 Qs total or something like that, but you will have a phase change problem on there, okay? And then general concepts, so conductors versus insulators, you know, temperature versus heat, all that good stuff, okay? So you want to be able to do all of that for me. So we're going to go over the concept map today, and then I'll let you guys work on the review sheet. And then you guys can bug me about any questions you have. And lastly, another thing I encouraged last period. So some of you guys got perfect 12 out of 12s on your quizzes yesterday. That's great. Some people were close. They weren't all the way there. And you may still not know exactly what you did wrong or what you should do differently next time. So if that's the case, bug me about it. Like, hey, Mr. P, I really thought this is how you did number 6. I don't understand what the problem is. So just let me know, okay? So I'll give you guys some time to look at those later today, too. All righty. Oh, there's Daniel. I recognize the Luis Suarez. There we go. Gotcha, Daniel. Boom. All right. Big Barca fan. All right. Here we go. Let's talk about the concept map. Again, this is printed off. This is like the second to last page of your packet. Okay? I had one girl last period like, wait, this was printed in our packet? I think right after I did the concept map. It's kind of funny. Anyways, so here's the point of a concept map. The reason why we do these is to sort of give you a visual of how everything's connected. So we've talked about a million things like kinetic energy, insulators, Q equals MC delta T, but it's like, so I know how to do all those things, Mr. P, but I don't really get why they're all in the same unit. Like, how are they connected? So the concept map is sort of there to show you the relationships of everything. Now, it all started with the law of conservation of energy. Somebody tell me what that is, by the way. What is that? The law of conservation of energy. Yes, sir? Energy cannot be created or destroyed. Just like mass can't be created or destroyed, energy can't be created or destroyed either. And so this is the big idea. This is the center of Unit 3. Everything flows out of the law of conservation of energy.
Hey, Mr. P.
Yes.
There's like a weird glare on the screen, so I can't really see what it's like.
Oh, weird. You know what? Why don't you try this? Hold on. I think I forgot to present. Let me see here. Present. If you pin the Mr. P now, does this look a little bit better?
Yeah.
There we go. I'm glad you brought that up. I forgot to hit the present button. Okay. So this also means that the heat loss must be equal to the heat gained. Okay. So when we take that super hot bolt and we put it in the water, it was hard for us to calculate how much energy the bolt lost, but we could easily calculate how much energy the water gained. And because of that, we then knew how much energy the bolt lost. So whenever anything loses energy, something else must have gained that energy. And we only can do that because of the law of conservation of energy lets us know energy doesn't disappear on us. And so the Q loss equals the Q gained. So we can set two Qs equal to each other if we know that energy was transferred between them. This is a really big idea. the Q equals Q. So Q to Q problems is what we call those. All right. So that brings us to heat. So we've said this term a lot, but let's make sure we remember the definition. Heat is the transfer of thermal energy. So this is when we're talking specifically about thermal energy transferring. And it is extensive, by the way. Remember, we have our high to low pictures that we'd always draw with the arrow, always going from high to low. That was heat. That was talking about transfer. Heat and transfer. Okay. Now the units on heat are joules or calories. You virtual folks, you know all about the calories from the food lab. You live folks will learn about calories tomorrow. Okay. If the calories even show up on the Unit 3 test, which they might, like one question, they're definitely going to be second fiddle to the joules. Absolutely. And remember, there's no such thing as cold, just removal of heat energy. It's like, oh gosh, the cold is getting through the holes in my jeans. But like, no, it's not. The heat is leaving your body through the holes in your jeans. And when your mom's like, Becky, please close that door. You're letting the cold in. But like, actually, Mom, I'm letting the heat out. Great, go to your room. All right, just make sure you understand cold isn't really a thing. It's just heat is either leaving or entering the situation. All right, and then we talked about specific heat capacity. Specific heat capacity. So this is the idea where, how much energy does it take to change 1 gram of a substance by 1 degree Celsius? Yeah, Mr. P, do I have to write down every word right there? No, you don't. But you do need to make sure you understand this idea. So water's heat capacity is 4.18. In other words, we got to shove 4.18 joules into a gram of water to make it go up 1 degree Celsius. That's what that means. And stuff with really high heat capacities may take a long time to heat up. Stuff with really low heat capacities may not take very long to heat up because they don't need that many joules to change your temperature. And it's represented by the C in the Q equals MC delta T equation. It's the cost to heat something. So it's the cost. And don't forget, it's a two-way street, so you can shove 4.18 joules into a gram of water to make it go up 1 degree. You can also take 4.18 joules out of a gram of water and make it go down a degree. All right. And don't forget, like I said, heat is extensive. The more stuff you have, the more heat it has. All things being the same. So if you have 1 ice cube versus 2 ice cubes, the 2 ice cubes have more heat. Okay? Because heat is extensive. It factors in the mass of something. All right. Then we talked about temperature. Temperature is the amount, the average amount of kinetic energy. It's an average. It's an average. And its units are in degrees Celsius. So I talked at the beginning of the unit. I was like, all right, I got a thermometer. Okay. Turn it on. All right. My thermometer says 22.6 degrees Celsius. And it's like, all right, nobody tell the thermometer. Nobody tell the thermometer. All right, I put it in the beaker. Oh, it's going to be so crazy. Shh, don't tell it's in a beaker. It doesn't know. It doesn't have any eyes. Oh, it still says 22.2. Like, the temperature is an average reading, okay? So it's not dependent on how much stuff you're reading. It just depends on the average, the overall ratio of kinetic energy per particle. So the higher temp means you have more energy and the particles are moving faster. Okay? So we know that kinetic energy is the energy of movement. And so the higher the temp, that means particles are moving faster. So water at 80 degrees is moving a lot faster than water at 7 degrees. That's what that means. Oh yeah, exciting times. And of course, lower means the exact opposite. Lower temp means something has less energy. It's moving slower. Yada, yada, yada. All right. Woo! A lot of writing. Stretch that paw out. Woo! Goodness. Get a little wrist stretch in there. There we go. There it is. Okay. All right. Now, thermal energy, aka the total amount of kinetic energy. So see how that's different than temperature. Temperature is the average amount of kinetic. This is the total. You're just adding up all the energy, and that's your thermal in a substance. And so that's our Q. So Q is the total thermal energy. It's just a grand total, all of the energy in a substance. So that's our Q. It's in joules. Yeah, it's the total amount of energy. Or it could be in calories. And we'll talk a little bit more about calories tomorrow, you live folks, when we do the lab. M is your mass in grams. C is your specific heat capacity. And delta T, of course, is your change in temperature. Change in temperature. Pretty good. Pretty good. All right. Now, let's talk about the different phases of matter, your solids, liquids, your gases, okay? Oh, let me bug someone. Let me see. Who's my victim going to be? Hey, Enders, can you hear me?
Yeah.
Yeah. She sounds nervous. Hey, solids, liquids, gas. Which one has the highest energy and which one has the lowest?
Gas has the highest and solid has the lowest.
Which one's moving the fastest?
The gas.
Love it. Pretty good. All right. So solids, they have a definite shape and volume, and they're just sort of vibrating in place. So I would go like this with my fists here. So it's not sitting still, but at the same time, it's not going anywhere. Okay, that's what solid particles are doing. If you pour an ice cube onto the floor, the ice cube won't take the shape of the floor. It'll just sort of sit there. So its volume is the same, doesn't change shape. Because the particles they don't have the ability to move around. They just have the ability to sort of shake or vibrate. Now liquids, okay, they can change shape. Not volume, but they can change shape. So if I pour liquid into a beaker, it'll take the shape of the beaker, but it'll still be 50 milliliters. If I pour it into an Erlenmeyer flask, it'll take the shape of the Erlenmeyer flask, but it'll still be 50 milliliters. If I pour the liquid onto the floor, it'll still be 50 milliliters, but it'll take the shape of the floor. And that's because liquid particles can sort of slide past each other. They can change shape because of that. We always talked about, after the bell rings, in between classes, how it's not like you're constantly running into people in the hallways. You just sort of slide past them. Like you're close to them, but you're like, wee, you're kind of bobbing and weaving in the hallways. It's pretty rare that two people actually just like run right into each other in the middle of the halls. I've seen it happen, okay? It's like the two people, neither one of them's looking around their surroundings, they're just looking at their phone. You can sort of see those people walking to each other. But anyways, liquids, generally speaking, they can change shape because they can sort of slide, the particles can slide past each other. And finally, gases, they'll change shape and volume, and they move independently. You pour some gas into a beaker, it will fill that whole beaker, and it'll take the shape of the beaker. You pour gas into an Erlenmeyer flask, it'll fill that whole Erlenmeyer flask, and it'll take its shape. You pour that same gas into the room, it'll take the shape and volume of the whole room. It'll just spread out as much as it can. Whew! Oh, that's a lot. And again, solids are low energy, gases are high energy. So as we go down this, we're talking about an increase in energy. Woo! Oh my, this is a lot of stuff. We covered a lot of stuff this unit. All right. So, let's always remember, energy does transfer from high to low. High to low what? High to low what? What's high? What's low? High to low temperature. That's right. Love that. Love it, Maddie. Yep. So something can have more energy. So an iceberg has more energy than a cup of hot tea. But if you pour the hot tea on the iceberg, the energy from the hot tea is going to go into the iceberg because the iceberg has a lower temperature. Even though the iceberg has more heat energy, it's got a lower temperature, and so that is what determines which way heat's going to go. Remember, conductors easily transfer energy. So if Austin over there were to take his paw and grab the wooden leg of his table, it wouldn't feel that cold, but if he grabbed the metal leg of his chair, it would feel very cold. Austin, why does the chair leg feel colder than the wooden leg?
Because the heat leaves in my hand faster. It's the conductor.
That's exactly right. Now, one thing to be careful of, and that means the chair leg resistor or insulator, by the way, which resists that energy transfer. Last period, I had someone say, like, hey, Mr. P, so should I think of conductors as cold and insulators as hot? Definitely not. Okay? Think of them as fast or slow. Conductors transfer energy fast or quickly. Insulators really slow it down. This is the same reason, like, if you touch the hood of a car in the summer, okay, it, like, burns your hand immediately because it's sending energy into your hand very quickly. So if a conductor's hotter than your hand, it will send energy in your hand like that, okay? So conductors aren't like cold, okay? They just transfer energy really quickly. It's just like a highway. Basically, think of a conductor as a highway. You can go two different ways on a highway, right? So if I'm on 71, I can go north or south, but it's really fast either way. Versus like, you know, a road in your neighborhood, okay? So you can go north or south on that road in your neighborhood, but it's just going to be a lot more slow. It's going to be more slowly than on a highway. Okay? Conductors, insulators. Endothermic energy is when energy goes in or enters the system. The products have more energy than the reactants, okay? Which makes sense. The stuff at the end has more energy than the stuff at the beginning when energy enters. Exothermic is the exact opposite. Energy is exiting the what? And this is from the perspective of the what again? It's energy is entering or exiting the system. It's the system. So always focus on the system. That's the chemicals or the reaction going down. Whew! And then we talked about entropy, baby. So this is when I first mentioned, all right, who's got a clean room? Who's got a messy room? Oh, let me guess here. Try to think about a messy room versus a clean room. You got a clean room? I knew it. I feel like she probably had a clean room. You? I bet you got a dirty room. No, really? Surprising. Interesting. I don't know why. Oh, that's right. You're totally right. I don't know why. Some kids are just like, oh, dirty room, clean room. And they're like, exact opposite. But then sometimes I'm not surprised. But yeah, if you have a really dirty room, like there's clothes all over the floor, that's a high entropy room. If you have a very clean room, organized, that's a very low entropy room. Solids are really low in entropy because they keep their same shape. They're not going anywhere. The particles are barely moving. Gases are really high entropy because they're freaking out. They're going all over the place really, really quickly. And so you need to be able to assess the entropy of a system. So if I'm like Billy, did the entropy increase or decrease in this reaction? You got to look like, okay, well, that was aqueous, that was gas. Like, you need to be able to assess that situation, talking about increase or decrease. And part of that reason is because of spontaneous reactions. So remember, something is spontaneous if it proceeds without you helping it. Can I erase it? Oh, disorder. Yeah. I was like, it's up there. I see what you're saying. So remember, if you like let's say Austin lights something on fire. Okay, so he had the light on fire, but if it keeps burning without him helping it, that means it's spontaneous. Or if you light a fuse and then something like a little firecracker goes off, that's a spontaneous reaction. So yes, you had to light it, but as long as it continues on its own without your help, it's spontaneous. What are the two things that the universe loves to spread? Heat and entropy, love it. So if a reaction spreads heat, that is, it's exothermic, energy exits the reaction and goes out into the universe. Or if it increases entropy, the universe loves that, and that will make it spontaneous. So if a reaction's happening spontaneously, it must be exothermic, or an increase in entropy. Or it might be both, but it's got to be at least one of these. We talked about NBA players, okay? If you're really tall and you're a great shooter, you're in the NBA. If you're really short and you can't shoot to save your life, you are definitely not in the NBA. If you're super, super tall but not a great shooter, you might be in the NBA. If you're not that tall but you're an amazing shooter, you might be in the NBA. Okay? So, with these spontaneous reactions, if it's both of these, it's spontaneous. If it's neither one of these, it's definitely not spontaneous. If it's one but not the other, it's a maybe. Okay? It's a maybe. Again, the NBA shooter are like, okay, you're not that tall, so you must be a great. If you're in the NBA and you're not that tall, you must be a great shooter. Does that kind of make sense? So if something's spontaneous and it's endothermic, for example, you'd be like, well, it must be an increase in entropy. There's no other way that's spontaneous unless one of these two things is true. So these work together sometimes, and sometimes they don't. Alrighty, and that brings us to our heating and cooling curve. Good times. So this one's specifically for water. So this is only for water right here. And so this first flat part is what temperature? Somebody tell me what temperature that first flat part is. 0. What about the second flat part? 100. Below 0 is a solid. At 0 means you're either melting or freezing. You're melting if you're going this way on the graph. You're freezing if you're going this way on the graph. Then it's all liquid. At 100 degrees, if you're going to the right, you're boiling, or you can say vaporizing. If you're going to the left, you're working your way down. That's condensing. And above 100 degrees for water means it's all gas.
Mr. P.
Yes.
So I got a 12 out of 12 test yesterday, but I got a little confused when it said, like, you go from 0 to 100. Why isn't that a 2-step process and it's only like a 1-step process?
Oh, that's a great question. I love that you asked that. The answer is that it might be. So if I'm asking you to go from 0 degrees here to here, that's a 1-step process. If I was asking you to go, hey, take some liquid water at 0, get it to 100 degrees, and then make it a gas, this second one would be a 2-step process. If it was like, hey, take some solid ice that's at 0 degrees Celsius, that would be here, and then get it to gas at 100 degrees, that would be 3 steps. So you have to go 1, 2, 3. So going from 0 to 100, if it's liquid the whole time, it's only 1 step. But it could be up to 2 or 3 steps. Does that kind of clarify there, Ms. Blacker?
Yeah, thank you.
Yeah. That question yesterday specifically said that it was liquid the whole time, so you're only going from here to here. So that's why that's a 1-step Q problem. Does that kind of make sense? Now, if I said take it to the steam, that would have been 2. So watch out for that. Watch that wording. Hey, McWigan, is this process, as you go this way on the graph, is that endothermic or exothermic? How do you know that? Yeah, generally speaking, the energy is going up, up, up as you move this way. So that one's endothermic, and this one's exothermic. You wouldn't see it heating up if you were just looking at this part of the graph, but since we can see the whole graph, we can tell, generally speaking, it's going up, and so that's endothermic. Yep. Pretty good, pretty good. Okay. So here is what I need from you. Virtual folks and live folks, go get your participation points in the Wednesday folder right now before you forget. You virtual folks, I would like to bug each one of you and see if you have any questions before you leave, so stay on the line. Live folks, get cooking on that Unit 3 review sheet, and I'll come see you guys after I mow down the virtual folks, okay?